Hello everyone, I'm Marlon. I'm a PhD student here in the group of Laura, and I will talk about one of my PhD projects, which is analyzing a lot of data from the Stockert telescope from this particular Magnetar. I want to start by again motivating why it is interesting to look at Magnetars. We already have seen this plot today in the talk by George, but I want to emphasize again that on this plot where you see the observed fluids, but distance and constant energies are on these lines. I don't know if you can see it in the back, but we have FRBs here on this corner here, and we have known neutron stars down here, and we have this SGR 1935 burst, which was observed by Chan and Statu. So if you now take this burst and move it further away, it will at constant energy will kind of merge with this bubble down here. So this links FRBs to something which we know of. We know kind of what a magnetar is. So this opens some questions. How does the emission mechanism work? Can we see some more FRB-like processes from galactic magnetars? And overall, how does the emission of magnetars change over time? Because we only rarely see, except just once, these kind of events. So a bit more on this magnetar. We have always seen a talk which is also dedicated to this magnetar in the infrared. So I always speak in the radio only, and there's only a few of the magnetars which are showing radio emission. I thought this number 6 from the magnetar catalog. I don't know if it's still up to date. There might be more, but it's just only a handful of magnetars. And it had an activity cycle from 2004 to 2008, just shortly after it was discovered. But it is active again 10 years after it turned off its radio emission. It was December 2018, which was also the beginning of the data set which I will analyze. So let's go on to the telescope. I'm sure most of you have not heard of the Stockert telescope before. It's this beautiful single-dish instrument here. It's the oldest radio telescope in Germany, and if you study at the university, you might do a lab course. And after some time, it was again refurbished, and nowadays it's completely run by amateurs. The real cool thing about them is they can just observe whatever they want. No need to write proposals, just observe. And so for my case, we observed at 1.4 gigahertz with 0.3 milliseconds. And as I told you, we can observe as much as they want. I have 350 observations with 1,000 hours of on-source time. So a lot of stuff to analyze. And what I did is something which typical FRB people do. I do some FI mitigation, I disperse the data, and then I search for single sources. Unfortunately, there's so many candidates, and in order to classify which one is real or which one is not, I used some neural network classifier, which is called fetch. It gives me some probability whether this is a real event or not. However, since it's a neural network, it can only be as good as the data which is used to train it. And so there's a very important limitation that frame below signal to noise of 8 is not it's not a complete set, because that was the limiting signal to noise for this training set. So let me make sure what I mean by what is a single pulse. I think most of people call other things single pulses, but when I speak of single pulses, I mean these things here. It's a millisecond event. It's not the entire emission of a rotation, it's just this event. There can be multiple ones in one single rotation, and they can come in all various shapes. I hope you can see that. Especially the beamer doesn't have such a nice color scale, but it can be just one of these very short events here. It can have a complex morphology. And after the classification, I found 58,000 of these events. So this gives a good range to do statistics, and I will show you some results later. And I'm focused on properties which you can directly see from these things. It's equal to noise, fluence, mean flux, and also width. But before we go into that, let's have a look at how typical repeaters look like. They can look like this. And these are very common things here, the so-called Saturn-Bone effect, which is seen in the frequency. But this is something I have not seen in any of these 58,000 single pulses. Obviously, I haven't looked at all of them manually, because that's way too much. But unfortunately, I have not seen this, and also I haven't seen something which is as energetic as an FRB from this market.
But if you just look at time series and forget about the limit spectrum, you might see some similarities, but that is just very weak. So let's have a look at how were the observations distributed in time and how active was the Magnetar. So as said, we started in December 2018. We saw something in the folded profile. Looks like this at this time. But we didn't see any single pulse activity here. There's just 20 single pulses before 2020. But after they stopped observation because here they could simply not detect the Magnetar anymore. We see a lot of single pulses. There are typically 100 or so within 1 hour of observation. And this also gives me all the 58,000 single pulses that I already had. For the rest of the talk, I'll focus on this later phase. Yes. So I have had an animation here, but it didn't survive the transfer of the computer. But it's good because I can talk on this a little bit more quietly without this moving. So what we did here is I take all the single pulses and group them together. Then I decide in what data range are they. These are the different colors. I will show all of them later on. And for the left case, I look at the single pulse width, plot them, and in fact, there seems to be some kind of distribution here, peaking at around 6 milliseconds. This dashed line here is my completeness threshold. I'm limited by the smearing on the low end. And there's also the completeness limit I mentioned, training sets, signal flows of 8, that you can transfer into affluence for a given width. So that means that some different fluences, different widths of single pulses drop out, which is very important when you want to interpret it, these kind of distributions, because fitting something to this data bar doesn't make sense when you don't have single pulses. So how does it look in time? Unfortunately, there's no animation here, so there's a lot of colorful lines here, but you have to trust me, there's a trend here. So from this blue thing, it moves from this only peak at 6 milliseconds, slowly to something which has a bimodal distribution with a second peak just before the completeness limit. Similarly, you see that the fluence distribution shifts from something here until 1000 jumps per milliseconds to something which is more narrow, which is connected to the width change of the single pulses. Because of the mean flux density, it remains roughly constant. One other thing which I did is I looked on where do single pulses occur within rotation. And for that, I basically looked on the phase. I made a histogram here for different single pulses. And within one of these date groups here, this is again the September 2020 events, I looked where do single pulses which are more narrow, between up to 1.3 milliseconds occur, and I see that they are very off from where the other single pulses occur. And this is also quite stable in time, and I hope this animation did survive. Yes, perfect. Yes, so once we start again, we can see that this off peak from the most narrow end is constant, and now we are in the phase where we have 2 peaks in the polar profile, and we see that while they are towards the end, in the time where we just had 1 peak, they are now in the middle or at the beginning of the second peak. And this offset of where different single pulses occur could be related to different regions where they're emitted. But yeah, if you have some more interpretation of that, then I think you guys give it more. We can discuss on what physics this could actually imply. And I want to conclude with some outlook. I just showed a few examples of what you can do with this great data set. You can do a lot of statistics here. You can also look at the waiting time distribution. You can also identify different single pulse population, for example, in the 2 peaks. And what I didn't show was you also have some evolution of the polar profile. And also why 58,000 single pulses might sound a lot. There's a lot more potential. If I'm able to lower the signal-to-noise threshold to 5, I can basically double the amount of single pulses. I have not talked much about implied physics, but I'm happy to discuss with other people. I have some ideas, but I'm not a theorist, so I'm happy for any input from theorists. And thank you for your attention.
Nice talk. I was just wondering if, I mean, these telescopes are really critical used to monitor all kinds of other, all the other magnetars coming to view. So, you might detect radio pulsations from previously radio quiet magnetars. Is that something that's being done, or are there plans to do that?
As far as I know, they only observe this particular magnetar, but yeah, this is something they can do. It's just a matter of it's people who have intentions, so you need some people who are at the telescope, you cannot steal it from home. Also, they need some money to operate. So if we give them some money, surely they will be happy to do this.
Wait,
Yeah, I was just wondering about your classifier. Do you use the abundance of pulses you've detected to train it? Is that how you train the classifier?
No, I have not retrained it. So this actually comes with some pre-trained models. I've used a combination of models which gave an accuracy of above 99%. But the good thing is it's a thing with a period. So I can also reject a lot of candidates where I see that the singles are always in the emission window where we expect them to be. And I also see that there are some limitations with this model. So it could be worth retraining it, but also since it's a thing which has a period and has some expected properties which I know from the other things, that is what I meant. I can maybe lower the signal noise threshold by applying the knowledge to a rerun.
Yeah, I have the same question. So can you say more about the limitations of pitch? Like, do you find pulses which are missed by pitch?
Yes, so I mentioned the signal to noise threshold of 8, that is one, but also it was only turned to 32 times series spin. So that's quite a limitation when you want to find very wide pulses. And also on the other hand, pitch is painfully slow for white first. So what I did instead is I knew where the pulse period is, and I get a list of all the white pulses which were found by the single pulse search, and then looked at them manually because I just saw edge is missing all of them. So if you use edge and you want to find white pulses, it's not a good thing. Look at them with some other thing.
can I ask, is there polarization information or?
Unfortunately, the current setup, Stockert's backend doesn't allow to do this. I think that will be very interesting to look at.
But there is no plan for.
I think it's again just a matter of manpower and money. I mean, it's not owned by us or someone else who has a lot of money. As people in the free time.